Okay, so we start with module 2. So the name of this module is logic family and logic gates. Again, it is a 4 hours. Again, will require 6 hours, might be, to finish this particular chapter. So 2.1, right now I'm not starting with 2.1. It is difference between analog and digital signal. So all the students roughly have an idea what is an analog and digital signal. So I'm not covering this. It's all theory. Then the logic, TL, CMOS, logic families and their characteristics. So I will be starting with 2.2 right now. Then I will go with 2.1. So 2.2, what is there in 2.2? It is digital logic gates, universal gates. Then realization using NAND and NOR gates. Algebra, De Morgan's theorem. Now, this is the building blocks of your digital circuits, because unless you know what are the logic gates, universal gates, then how do you realize using NAND and NOR gates? And also you should be knowing Boolean algebra and De Morgan's theorem. So this will help you in understanding all the remaining chapters of digital circuits. So it is quite interesting and simple, but you have to remember some things. Okay, so we start with, write down the topic, logic family and logic gates. That is module 2. We are starting with digital logic gates. Okay, so as such, it is 2 hours, but 2 hours is not sufficient because you will be drawing. Many things are there which you will be seeing for the first time. So you need to write also those things. Now, what is logic gates? Logic. Okay, logic gates is a very important concept in the circuit design and digital system. Here you can see it is a building block of digital system and an electronic circuit that have only one output. So I can have many inputs, many types of input signals might be there, but the output is only one. Okay, so this is a special case, okay, where I have only one output. So these gates can have one input or more than one input, but most of the gates have inputs in such one input we won't give, but output will be one. That is what is the speciality of logic gates. Now, on the basis of the relation between the input and the output, okay, so I give a certain set of inputs. Inputs will be ones and zeros because it is digital. What will be my output? So some names we give based on the combination of input and output. So some of the names, the common name is AND. So AND gate, we have OR gate, and we have NOT gate. These are the new names. Now how these names are coming? On a certain set of input, I get a particular output. Okay. In the nature of that output, we give all these names. So right now, from this particular slide, you learn 3 gates: AND gate, OR gate, and a NOT gate. Now, what are these gates? Gates are some circuits, digital circuits, where you give some combination of input and you get some combination of output. So that is, we call it as a gate. Okay, so gate means somebody comes inside and somebody goes outside. No, so it is allowing entry and exit. So that's why the name gate is there. And based on, again, the input and output relation, we have given some names. Okay, so we will see what are those, why those names are given. So let us study different types of gates. Those are basically IC. Okay, so जैसे तुम्हारा capacitor रहता है, inductor है. So gates are some types of ICs, 8 pins, 16 pins, and so on. Depends the type of IC that you are selecting. So first one, we start with an AND gate. Okay, so write down this name. What is an AND gate? Okay, the output of an AND gate will always be low when any of the input state is low. Okay, so ANDing operation. Now, what is ANDing operation? At the input, if any of my inputs, suppose there are 5 inputs or 2 input or 3 input, if of the input is low, the output is always low. Means agar koi bhi input 0 hai, okay, any one of the input, your output will be 0. Low means 0, high means it is 1. So If any input value in an AND gate is set to 0, then it will always return a 0 value. Okay, so you are having logic level 0 in any of the input combination, your output will be logic 0. Okay.
0.
Okay, so this is the sentence that you write. And how do I represent it? ANDing operation agar hum dikha rahe, like for multiplication you have that multiplication symbol, for division you have that symbol. For ANDing it is how do, suppose I have two inputs A and B, and Y is my output, so A dot B is equal to Y. So represents the, or you can say full stop, a single dot represents the ANDing operation. So A dot B is equal to Y, where A is one of the input, B is my second input, and my output is Y. So this is how I represent an ANDing function. Now, this symbol. Okay, so the logic design for an AND, please draw this. Please draw the exact, don't make it a triangle. Okay, so this is my AND gate. I have two inputs over here, A and B, and this is my output Y. Okay, so it is a two input AND gate. So if they ask you what is the symbol or logic design of an AND gate, so this is my two input AND gate. And then comes the truth table. Now what is the truth table is, based on input combination, what is the output? Now just now we have defined over here is, if any input value in an AND gate is set to 0, output is a 0 value. So based on this logic, we will write the truth table. Now since I have two inputs over here, so 2 raised to 2 in binary, I will have 4 combination. So 0, 0, 0, 1, 1, 0, 1, 1. So these are my input combination. Okay, I can give that input combination. Now here both the input is 0. So 0 into 0 is 0. Here 0 into 1 is 0. Any one input is 0. Here again one input is 0. So 1 into 0 is 0. Here none of the input is 0. Means all are high. Logic 1. So you can say 1 into 1 is 1. Okay, so you can follow the simple multiplication operation that is in ANDing. So 0 into 0 is 0. 0 into 1 is 1. 1 into 0 is 0. 1 into 1 is 1. Because anything multiplied by 0 is 0. So that is what is used in an ANDing operation. Any one input is 0. My output is a 0. Okay, so draw this truth table nicely, because if a theory question comes, they will tell you to draw the symbol and the truth table. So this word is new, and we will be using this frequently, because for any digital family or logic gates, everything is dependent on the truth table. So you should be knowing the truth table. Okay. So this combination should be on your lips: 0, 0, 0, 1, 1, 0, 1, 1. And this is A into B. You can put a dot over here. So that is showing you the ANDing operation AB. So 0, 0, 0, 1. So this is the simplest example where I am taking two input. You can have input AND gate, a 4 input AND gate, and so on. You finished with this?
Yes, ma'am.
Okay, so here we have a 3 input AND gate. So I have A, B, C, and here you can put Y as the output, and then 2 raised to 3. So 8 combinations of input I will have. So you quickly write down A, B, C.
Okay, ma'am.
0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Wherever there is even a single 0, your output is 0. Wherever all ones you have, all inputs are 1, at that time you get a 1. Okay, so there might be some operations where you require to give a signal when all the levels of that, suppose a tank is there, when all the tanks are full, 3 tanks are there, up to at the time a signal will be generated. Any one of the tank is not full, the signal or the indicator will give you a 0. So wherever you require such application, you can use a simple AND gate. So what you have to do is the circuit is already built, that IC is already built. You have to give a VCC supply, a ground connection,
Ground connection.
give ABC from the input wherever is the input source, and then the output. You give it to a, if you want to connect it to an LED, you connect it to an LED. Okay. And then you can see if the LED is off, means the output is 0. If the LED is on,
0.
it is 1. Now, usually the AND gate that we will be using, please write down the name. It will be the TTL family. That is transistor logic. Okay. One was that TTL and CMOS. When I make an AND gate, I can make it using many things. So initially, when only transistor was there, all these ICs, see all these functions they are doing, no, multiplication and all this. So inside I have transistors doing all these operations. Okay, so that's why they belong to TTL family, that is transistor logic. Now, later on, when VLSI and everything was developed, the CMOS technology came. Okay, so the same circuit operation outside, input and output will be same, but inside the components, it will be all your CMOS devices. Now, why we go for CMOS? Because they might be faster. Okay, the delay, see when I give an input, there might be little delay in getting the output. Okay, so all those delay parameters and all are improved in case of your CMOS ICs. So we have the TTL family and the CMOS family. In lab, whenever we are doing the practical, we will be using all our TTL gates. Okay, so there is a series by which you identify when you ask for the gates to do the practical in lab. You have to tell, okay, mujhe ye 7401 IC do, 7402. So that 74 series, TTL series. Okay. So clear about the AND gate?
Yes, ma'am.
You have written this table?
Yes, ma'am.
Oh, don't skip this table, because now this, for every there's 2 chapters, you have to keep on drawing this truth table. Without that, we cannot proceed. Now, this was the first gate, that is my AND gate. The second one is an OR gate. Okay, now OR gate is also mostly used in digital logic circuit. Now, what is the OR gate? The output state of the OR gate will always be low when both of the input state is low. Means if any of my input is 1, I will get at the output 1. Only I have 2 zeros, means all my inputs are 0, that is low, and my output is low. So if any input value in an OR gate is set to 1, then its output is always 1. And how do I represent an OR gate? It is with the symbol of a plus sign. So A plus B is equal to Y. ANDing was A dot B, that is a multiplication kind of thing, is equal to Y. And ORing is an addition kind of thing. So OR ka symbol is plus. So we call it, we will not call it A plus B, we will call it A or B, but in mind it is actually plus. So your OR is, any one input is 1, the output is always 1. And when all the inputs are 0, the output is 0. And we are using the addition operation in case of an OR gate, that is A plus B is equal to 1. Now the logic design, the symbol for an OR gate is something like this, a curve. Inside jo bhi likha hai na, wo mat likhna. Okay. Whatever is written inside, it is not required. So OR, this is the symbol. Okay. Yahan pe curve banana, do it the way it is drawn. Okay. Many times the students draw any symbol. Koi rectangle bana dete something. So yahan pe aisa corner banao. And here there is a curve. Again, we are taking 2 inputs, A and B. And my output, I am denoting it as Y. So this is my symbol or logic design. And if I see the truth table, okay, 0, 0, 0, 1, 1, 0, 1, 1. So this is my input combination. Now, whenever both the inputs are low, that is 0, 0, obviously you can say 0 plus 0 is 0. Okay, that way also you can consider. 0 plus 1 is 1. 1 plus 0 is 1. Now, yahan pe, if you go to the simple binary addition that we studied in the last chapter, 1 plus 1 was 0 carry 1. ऐसा नहीं है.
Yeah, yeah.
Any one input is
That is
1, my output is 1. यहाँ तो दो input 1 है, so my output is 1.
1.
So both the inputs low, my output is low. When any of the input is high, that is 1. Yeah, it is 1. See, in some of the books which you will read, instead of 0, they will use L. Instead of 1, they will use H. Okay, so
Okay.
H hai. Okay, so
Okay.
you realize realization is a little bit difficult when you use only low and high signal. So we convenient mostly by writing
low,
zeros
low.
and 1.
1. Okay.
Okay, so this is your 2 input OR gate. So basically for ANDing, we use multiplication somewhat relation, and for ORing, we use addition relation. That's why the symbol was plus. Only in this case, you have to remember 1 plus 1 is not 0 carry 1. And 1 plus 1 is 1.
Yes,
Finished?
yeah, finished.
Now let us draw a 3 input OR gate. So I take A, B, C, my output is Y. Without seeing this table, okay, that is easy. Only when all my input is 0, output is 0. Any of the 1, my output is 1. So this is my 3 input OR gate. So you should be very fast in writing this combination. You can put 4 zeros, 4 ones over here, then 0, 0, 0, 1, 1, 0, 1, 1. Again 0, 0, 0, 1, 1, 0, 1, 1. Okay, so chances of doing a mistake is less. So 3 inputs, ABC, 4 zeros, 4, 1. Or you can remember, ये तो easy है 0, 0, 0, 1, 1, 0, 1, 1. Or you still want to remember more easily 4 zeros, then you have 2 zeros, 2, 1, 2 zeros, 2, 1. 0, 1, 0, 1. The last column is 0, 1, 0. It starts with 0 and 0, 1, 0, 1 alternate. So you start with all zeros and you end up with all ones. So that way also, because see, in exam you have to write this truth table. Not only this, other circuits also, you have this truth table. So where usually go with 3 inputs, because 4 input it becomes 16 combination. So you should write this thing fast. Then you have to decide what happens to this particular parameter.
Yeah, yes, ma'am.
Once you finish it, you tell me.
Yes, ma'am. Right. Hello. Yes, ma'am.
Finished? Yeah.
Yeah.
Next comes the third gate. So we studied AND gate, we studied OR gate. The third one is the NOT gate. Okay. So NOT gate is having again 2 names, inverter or an inverting buffer. Now from this is the most basic logic gate. So actually before AND and your OR NOT came into picture. And it is an inverter or an inverter IC. Inverter IC means here this NOT gate has only one input and one output. Whatever AND or OR gate we studied just now, they required minimum 2 input. Okay. And there was an output. But NOT gate, it requires only 1 input and I have only 1 output. Okay. Now since it is an inverter, what is the function? If I have 1 at the input, I get 0 at the output.
0
Get 1 at the 0 at the input, I get 1 as the output. So many times when I say yes, you say no. We say, "Are inverter IC hai kya between?" Because our ideas are totally opposite, 180 degree. So that is what is your NOR gate. When I give 1 as the input, I get 0 as the output. When I get 0 as the input, I get 1 as the output. So it is complementing it. मतलब उल्टा कर रहा है. So my symbol is, I will not have a B term now because I have only 1 input. Suppose my input is A. Now What will be my output? Y output is A dash. A dash
Output is A
matlab
dash.
complement of A. So when
Complement of
A is not true, then Y is true.
Okay.
Okay, so A is 0, then Y is 1. Okay, A is 1, then Y is 0. So that is what is
Yeah.
the meaning of a
Yeah.
and not
Not
operation.
good.
Now the standard NOT gate is given a symbol that is shaped like a triangle with a circle at the end. Now see here I am showing you the previous two ICs again. यहाँ और गेट था. Okay, so you had this curve, you had this curve, and ये output. यहाँ bubble न भी draw करो तो भी चलेगा. Okay, this is my output knob. This is my input knob. I am showing you an AND gate. Okay, so you had the input at the output immediately. यहाँ से don't draw the line from here or here. Exactly from the center, you have drawn a line. Here is my Y. Now, here this sentence states that it is given by a symbol. See, abhi tak we never discussed this point about. I had just showed you the symbol. It is shaped like a triangle with a circle at the end point. Okay. So once the triangle ends, there is that bubble kind of thing. Okay. I'll show you the symbol. That circle shows you the invert operation. That is the ulta.
That is invert.
When I draw a triangle, here you can see immediately there is a bubble over here. ये तुम्हारे AND gate में भी नहीं था, nor not ये OR gate में भी नहीं था. Okay, so this bubble shows you the invert operation. Means 1 ka 0, 0 ka 1. So I have one input A and here make the output as Y instead of B. So 0 ka output is 1, 1 ka output is 0. So don't forget to draw this bubble, otherwise it is not an inverter circuit. The logic design.
What will be? If it is not having that 0, then
pardon?
If it
the
doesn't
bubble
have that
means
bubble,
it is not the symbol of a NOT gate. So we don't know what is that operation because there is no symbol in logic family with just a triangle. Okay, so if you don't draw this, means it is not an inverter IC because sometimes students forget to draw it and means the exam हाँ वो गलती से हो जाता है वो हमें समझता है but it does not represent inverter operation. So suppose AND gate का भी तुम्हें invert करना है. Okay, so you show a bubble there. Okay, OR gate का भी तुम्हें invert operation दिखाना है. Like suppose I just show you because that IC will come later on, but I'll suppose you bubble over here. Okay. तो ये क्या हो गया इन्वर्टेड और गेट हो गया अगर यहाँ पे बबल डाला तो ओके वेयर माय पॉइंटर इज तो यहाँ पे क्या हो जाएगा जहाँ पे भी 0 आया था आउटपुट हियर इट विल बी 1 एंड हियर इट विल बी ऑल zeros. So this was my actual OR gate का truth table, but the moment I place a bubble over here means वो invert over. Okay, this truth table will be modified. Wherever there is a 0, it will be 1. Wherever there is a 1, there will be a 0. With an AND gate, this was my normal AND gate. But suppose if there are ICs available, you will see what is that name. Inverted AND gate. Okay, so I put a bubble over here at the output. Okay, so this relation will be inverted. So जहाँ पे भी 0 था, सारा 1 1 1 हो जाएगा. And wherever there was a 1, it will be 0. Okay, so this will be an inverted AND gate. This will be an inverted OR gate if a bubble is placed. But we will not call it as an inverted AND or inverted OR. We will give a different name. In short, I want to tell you that you have to remember this bubble. This bubble indicates it's an inverter gate. Clear?
Yeah.
Okay, and there will be only one input. Now comes, you have to understand this, the NAND gate. Okay, NAND. So AND name is already there. Now under the category of NAND, I will again come back to this topic when there is a topic in your syllabus, universal gate. NAND is one, there are two universal gate, NAND and NOR. Abhi OR sikha and AND sikha. So if I add N to it, so it becomes NAND and NOR. So NAND and NOR are universal gate. Now what is universal gate? I have three basic gates, that is AND, OR and NOT. Okay. So 3 basic gates are there. Okay, so I have this basic gates which are performing OR operation, NOT operation, and operation. Okay, but there is a gate. Suppose I give it a name right now, NAND. I can implement all these functions using a NAND gate. Okay, जैसे AND का IC मैंने तुम्हें दिया and I tell you
सब उसमें ही है.
हाँ, if I tell you कि AND gate दिया, but I tell you I want OR का operation. So using AND I cannot make an OR gate. Or if I give you OR का IC, I tell you कि no, I want AND gate. Do something with that IC, do the connection or equation, do something and make that OR gate function as a NAND gate. It is not possible.
Not possible.
Gates. But I have another gate, another IC, which I give it a name NAND. I can implement any of these and or not using a NAND gate. That's why this NAND and NOR are called as universal gates. So a short question of 2 marks or 5 marks might come in the exam, which comes in the exam. Why NAND and NOR gates are called as universal gates? So why gates? Because we can construct any basic gate such as and, or, and not. So these are my 3 basic gates, using NAND gate or a NOR gate. Okay, so that's why they are given the name universal gate. So we will be seeing tomorrow in the next lecture how we can make an AND gate using a NAND, OR gate using a NAND, NOT gate using a NAND. So that question is also comes in the exam. Okay, so NAND, the name comes, not AND. Okay, so AND you already know now. Now that N stands for not AND. Means you know the operation of an AND gate. Any one of the input was 0. My output was 0. That was 0. Operation. Now यहाँ पे उल्टा हो जाएगा because that inverter function not gate is AND. So my output stage of a NAND gate will be low when all the inputs are high. See, AND gate में क्या था? When all the inputs were high, at that time my output was high. In case of a NAND gate, यहाँ पे क्या होगा? In case of an AND gate, in case of a NAND gate उल्टा होगा. My output will be low when all the inputs are high. Means whatever was the complement of an AND gate, I will get. So AND gate का result था exactly opposite of it will be my NAND gate because NAND is not plus an AND gate. So we know the symbol of an AND gate was A dot B. So why was A dot B? That is my simple multiplication. But I am getting reverse function of it. We call it as by complement. So complement के लिए we put a dash over here. So A dot B, the complement of it. See, in some books, there will be a dash like this, or there might be, let me try to, I don't know how to write. Or it might be like this, a bar.
Okay.
So I don't put both, a bar also or dash also. So I A dot B also inverted comma like this or A dot B uske upar bar means it shows the complement operation. So AND was A dot B, NAND will be A dot B complement and the value of Y will be true when any of the input is set to 0. Okay, so let us draw the truth table and the symbol of an NAND gate. So NAND gate, here is a 2-input NAND gate. So the symbol of a NAND gate, first draw this symbol. Don't draw this ANDing operation here. So here remember to draw a bubble. Without that bubble, it is a simple AND gate. देखो ये वाला bubble तुम ना भी draw करो तो भी चलेगा. Okay. A or B, if you just draw 2 lines, Y 2 line, Y just a line, it is okay. Okay. For an AND gate, this bubble should be there. So it is a 2-input NAND gate. I want to actually show you the combination. It is AND plus NOT. So I have the ANDing operation. So A, B, AND gate gave me A dot B. and inverted one will give complement of A
Complement
dot
of
B.
A and
So
dot
A
B.
dot B
Okay.
complement. So either a dash or a line over here.
Okay.
So AND gate, AND plus NOT gives you NAND. And truth table you can see for AND gate when both the inputs were
Yeah, both are first
output was 1.
on
But here
one
it is
zero.
totally ulta.
Okay, ma'am.
So AND gate, if you want to remember the truth table, remember AND और उसका उल्टा लिख देना.
Okay.
Or remember when both the inputs are high at that time my output is low.
Low.
Okay.
Yeah.
Or you can say 0 into 0 is 0, but complement of 0 is 1. 0 into 1 is 0. Complement of, because this is complement symbol. So 0 ka complement 1. 1 into 0 is 0. 0 ka complement 1.
Yes,
1 into 1 is 1.
1.
Uska complement is 0. So this is how you can write the truth table. Because AB is multiplication and uska complement.
Uska complement. Yeah. Yes, ma'am. Then. Yes, ma'am. Done.
Okay. So this is suppose my 3 input NAND gate. So I have A, B, C
Okay.
and
Yeah.
below is over here. Now the logic is how any of the input is 0. In AND gate, output was 0. So here when all the inputs are 1 at that time my output is low.
Low.
I'm not getting all ones. Okay, in any of
Yeah.
this combination, I'm not getting all ones. So my output is 1.
Output is 1.
When I have all the input as
one,
high or
0.
1 at that time, my output is low. So exactly the opposite of 3 input AND gate, we get the output of 3 input NAND gate. So if the question comes, why NAND and NOR are called as universal gates? So you can draw the truth table and later on I'll show you the example. That is a question how you can implement and or and not using NAND gate. So that I see. So for that you should be knowing this circuit output combination. Then only, because it will not be a single NAND gate, you have to use many combinations of NAND gate to get that or and not.
And then not. Okay. Yes, ma'am. Done. Yes, ma'am. Done.
Once you finish, you tell me.
Yeah, I'm done.
Finished?
Yeah.
Finished?
Yeah, ma'am. Yeah. Finished.
Okay, I'm waiting for you. Okay, the next
Yeah,
one is my NOR gate. So NOR, as I said, NAND and NOR, those are two universal gates. So using NOR also we can realize all the basic gate. So NOR is a combination of NOT and OR gate. Okay, so NAND was not an
Yeah.
and NOR is not an OR. So we will
Okay.
exactly the opposite of an OR gate over here. So the output state of a NOR gate will be high only when all of the inputs are low.
No. Okay, ma'am.
Okay, so what we were getting in OR gate, any one input is one,
No, one. Yeah.
only when
One.
we had a combination 0
Combination,
0 at that
okay.
time my output was 0. Okay,
Zero.
so
Yeah.
here the output of a NAND gate here will be high instead of 0 when all of the inputs are 0. So NOT gate, when I have both the input as 0, at that time my output will be
Output is
high,
zero.
and
Okay,
I
ma'am.
get exactly the complement result of an OR gate. So if I want to write the logical or Boolean expression for a NOR gate, see all these expressions are important. So we call it as the logical operation or the Boolean expression.
Volume
So
expression.
opposite of OR operation. So OR was A plus B
A plus B.
and the whole
That's the
complement of it.
complement.
Please don't forget to
Uh-huh.
put the bracket.
Yeah.
Otherwise, if you simply put a dash over here, it will look only complement of B.
B of B.
But what we
Yeah.
are doing, we are ORing it and the whole complement of
And
it. So the value of Y will be true when all of your inputs are set to 0. For OR gate, when all my input was 0, the output was 0. Huh? But here my output is 1. True means 1.
Yes, very high.
Okay.
Yeah.
So if I write, we have written the expression. So if I write the truth table symbol, you will draw it. So 0, 0. My output in OR gate, it was 0 plus 0 is 0. But here I will
0.
1 because, and यहाँ पे A plus B complement लिखना, हाँ? B A plus B complement, यहाँ पे भी A plus B. It is, they have used the same notation, but you will draw it correctly.
Yes, ma'am.
Okay, so this is my OR ka symbol and I'll place a bubble over here. So this becomes my NOR.
No.
It is an two input NOR gate. It is not AND gate. Two input NOR gate. So it is OR plus NOT. This is OR. Instead of AND, you write it OR. And यहाँ multiplication का symbol है, put a plus over there. यहाँ पे भी plus, यहाँ पे भी plus का symbol.
Yes, ma'am.
ये inside whatever is written, no need to write with this. Just remember, put A plus B complement of it. So the symbol comes A plus B, the whole complement.
Okay.
So whenever my both the inputs are 0 at that time, I get output high. So that is my NOR gate.
Okay, ma'am.
So 0 plus 0 is 0, but complement of it will give me 1. 0 plus is 1, but complement of it will give me 0. 1 plus 0 is 1, but complement of 1 will give me 0. 1 plus 1 is 1, and complement of 1 is 0. So this way you can remember the truth table so of a NOR gate. Now, what will be for a 3-input NOR gate? So I have the symbol 3-input NOR gate. So when all the inputs are 0 at that time, my output is 1. Okay, wherever I have any one input not 0. Okay, so here I had 1, 2 combinations. Here I had 2 combinations of ones. So at that time, all my output is 0.
Yeah.
Just a moment, we'll see the this we will be finishing till this only.
Yes, sir.
So 5 ICs we
Okay.
studied, and or,
Yeah.
not,
And
then
NOR,
NAND and NOR.
NOR.
So out of all these 5, NAND and NOR are called as universal gates or universal ICs, because any function basic gates I can implement using NAND and NOR. So this is something you should not forget throughout now, since you become an EXTC engineer, that these are universal gates. Now, how we can do it, we will see that combination. Now, once you understand that, because in a first practical is when hard practical is verification of the truth table of all these ICs. So we give you a NAND IC, we give you a, we give you and, or, and not. So 5 ICs we give you, and 2 input IC is there, 2 input NAND gate, NOR gate, and OR. And then what you have to do, you have to verify the truth table.
Okay.
So that is what is the first practical of your subject. So you go to lab, you do the connection, the IC, you mount it on the breadboard, you give, so the IC pin diagram is there in the lab, they give you the handout. So you know which pin, because it will be not only one IC will be there, it will, in a single IC, 4 gates will be present. Okay, so I can have A, B, and then one output, then C, D, one output, E, F. So 4 gates will be there. Okay, so you can use any one combination. So you need to know which pin is my VCC, which pin is my ground, because all these ICs will work with some amount of supply, no, because the transistor inside should be switched on. Okay, so we give for TTL family, we have to give 5 volt. So from the battery, we give 5 volt. We should not exceed 5 volt. Okay, and 5 volt and ground we connect to those pin. And यहाँ पे क्या करेंगे, high input देंगे. Means when I say 1, means it is 5 volt. Okay, so 1 over here, this is my output. Okay, so either you connect an LED at the output or you connect a multimeter. Okay, suppose LED nahi hai lab mein. So what we will do at the output, we will connect a multimeter now. Okay, so multimeter 1 point I will keep it over here, and 1 point I will connect it jahan pe bhi ground hai or supply ka ground hai, I will put another knob over there. So if I am supposed to get a 0 voltage, multimeter will show me 0.2 or whatever, some value of 0. Wherever I am supposed to get 1, I should be getting approximately 5 voltage. So exact 5 to nahi, 4.2, 4.4, depending upon the IC. Okay, but ideally it should be 5 volt. Okay, so what verification of truth table, यहाँ पे तुम 0 voltage दोगे, means you can directly connect 2 input. If I am discussing, I'll show you this. So you give 0 as the input, but you can see that at the output the LED is on. Okay, means I am verifying the truth table. That is your first practical. Then you give 1 0, यहाँ पे 0 दे दो, यहाँ पे 1 मतलब you will connect 5 volt over here. So जहाँ पे भी 5 volt का बैटरी है, वहां से एक वायर लेके you will connect it to this pin, and the output you can see that LED जो पहले on था, now it is showing that it is a 0 state. If you feel कि अरे LED जल गया, उसके लिए 0 दिखा रहा है, you measure the voltage with a multimeter. Okay, so that is also possible, because sometimes the students, if they are not getting the output, वो लोग wire निकाल ही देते हैं. So by default the LED does not glow. Okay, so some might feel कि हाँ ठीक है 0 output आ रहा है, because this is what you have to show it to the examiner. They tell you to measure it with a multimeter. Then you reverse 1 0 दे दो, the output will be 0. Then you give both high. You apply 5 volt over here, 5 volt over here. Okay, just using a wire you will connect, because already 5 volt you have given somewhere in the IC. Okay, so from there you connect a wire, and the pin numbers will be there, because as I said, in one IC there will be 4 gates present. Okay, हर एक gate में 3 चाहिए. So 3 4s are 12, and then you have one for VCC, one for ground. So it will be a 14 pin IC. Okay. So this is how you verify the truth table. So similarly, we will give you a NAND gate, and then again you will verify the truth table. So this is your first practical, that is verifying the truth table of the basic gates. The second practical is you will be implementing, that is realization of NAND and NOR as the universal gate. Okay, so realization means using NAND gate. I will teach you that you have to implement a NOT gate using NAND.
Not and all. Okay.
Using NOR. Similarly, you will implement an OR gate using NAND. You will implement an OR gate using NOR. So some combinations of circuits are there, and that is you have to show us the result. Okay, so that was second practical. So I don't know whether we will be performing those practicals because simulation it is difficult. Still, we will try.
Okay.